Welcome back. Let's look at a couple of applications. Consider an economy with three sectors: chemicals, fuels, and machinery. Chemicals sell 30% of its output to fuels, 40% to machinery, and retains the rest. Fuels sell 80% of its output to chemicals, 10% to machinery, and retains the rest. Finally, machinery sells 20% of its output to chemicals, 20% to fuels, and retains the rest. Okay, so I'm going to make a purchase by list here: chemicals, fuels, and machinery. Chemicals sells 30% to fuels. Chemicals sells 30% to fuels. We're just kind of like doing the crosshairs: column, row. 40% to machinery, and retains the rest. Well, these two make up 70%, so they would retain 30%. Fuels sells 80% to chemicals, 10% to machinery, which would leave 10% to itself. And then finally, machinery sells 20% of its output to chemicals, 20% to fuels, and retains the rest. Well, 20 and 20 make 40%, so it retains 60%. I'm going to let these subscripts C, F, and M represent chemicals, fuels, and machineries. So we're going to set up these purchases where we have 30% for chemicals, 80% for fuels, 20% for machinery. Notice that we have 3 rows and 3 columns. 3 rows and 3 columns. The chemical column has all the PCs. The fuels column has all the PFs, and so forth. So we're going to set up a homogeneous augmented matrix, which will be all set equal to 0, and we'll have a 0 column. Okay, so let's set this up. Also notice down here we have a negative 0.7 PC. These three are to identify the rows: purchases by chemicals, fuels, and machinery. This isn't 1. If we bring this 1 over here and match it up with its like term, a 1, when it crosses, makes a negative 1. 0.3 minus 1, that's where I'm getting this negative 0.7. Notice the 0.8 and the 0.2 stay the same. PF, 1 PF, there's its like term over here. So if I subtract 1, 0.1 minus 1 is where this negative 0.9 comes in. Again, 0.3 stays the same, 0.2 stays the same. Third row, if I bring PM over, 0.6 minus 1 is where this negative 0.4. That's kind of a hard part when you're doing this problem, is to remember, after you've set your 3 rows and columns equal to 0, because you will set it up as a homogeneous, where it's all accounted for, balanced out. Remember to bring these over and subtract. That's why these 3 values on the diagonal don't look the same. It's because they've all had 1 subtracted. Okay, so I feel like I'm beating a dead horse there, but now, once you've got all your terms collected, take each column, set it up as an augmented matrix, row reduced echelon form. From that augmented matrix, we've got a row 3 that's all zeros, so that tells us the machinery is free, because machinery was that third column. Chemicals is equal to positive, remember to take that over, positive 34/39 machinery of the machinery. Fuels is positive 20 over 39 times PM. Find a set of equilibrium prices when the price for machinery output is 30 units. So they're giving us a value for PM. Okay, so for chemicals, 34 over 39 times 30 comes out to about 26.2. And then PF, when 30 is subbed in, 20 over 39 times 30 is about 15.4. The hardest part is getting that set up correctly. And then row reducing, you can use your calculator, convert to fraction. All right, the application section in chapter 1, I kept it pretty brief. There's one example where we just did one with the chemicals, fuels, and machinery. So that's why I did this example, so you'd have one for your notes to check out, and hopefully it'll help you through yours. My math lab also has help features, so you should be fine between these videos. Of course, you always can ask me for help. That's my job, is to help you as much as I can. Let's move on to another example. The second example is a general flow pattern for a network. We're going to assume all flows are non-negative. What's the largest possible value for X3? Now I've tried to sketch in these arrows to show you the direction of the flows. There's 3 junctions or nodes, A, B, and C. So I went ahead and labeled those. For each junction or node, we're going to do a flow in and a flow out. For A, X1 flows in, X3 flows in, but the outflow is 50. Okay, so the inflows are X1 plus X3. The outward flow is 50. For B, there's an inflow of X2. Outflow is X3 and X4. X3 and X4. They both go away from node B. And then finally, junction C, there's an inflow of 110. Outflow is X1 and X2. For the network overall, just the grand scheme of it, 110 is going in, 50 and X4 are going out. So we have an inflow of 110 that has to equal the total of 50 and X4. And that's why I set this up. The inflow and outflow, if it's going to be an equilibrium, have to match. So the amount coming in, the amount going out, that tells us if we subtract 50 from both sides that X4 has to be 60. Okay, so X4 is equal to 60. Let's set all this up. Junction A, we had a flow in of X1 plus X3, an outflow of 50. Your flow out will have a column of its own. Let's see, X4 was equal to 60. X1 plus X2 is equal to 110. And X3 plus X4 is equal to X2. Now, if we were to put them all on the same side, X2, remember we're setting these equal, flow in, flow out. X1 plus X3 is equal to 50. X2, if it's equal to those, we can bring X3 and X4 over. They'll go from positive to negative when you bring them across the equation. But if you bring these two over and pair them with that x2, then the flow out becomes a 0 because you've moved those two terms over. Flow out equals flow in, x1 plus x2 equals 110. And then again, x4 we determined to be 60. We are going to have a 4 by 4 matrix. X1s make up your first column. That's 1, 1, 0, 0. 1, 1, 0, 0. The X2 column is 0, 1, 1, 0. 0, 1, 1, 0. Third column is 1, 0, negative 1. Let me fill these in real quick for you. And 0. And then the fourth column is 0, 0, negative 1, 1. 0, 0, negative 1, 1. And then these constant values, 50, 110, 0, and 60. Row reduced echelon form. X4 is equal to 60, which we already determined up here. So X4 equals 60. X3 is free. X2 is going to be 60 plus X3. I'm going to go ahead and move to the next slide. X1 is going to be 50 minus X3. So when you move all these over, X1 is 50 minus X3. X2 is 60 plus X3. X4 was fixed from the overall diagram. And then remember, X3 is free. Now, if you look at each component, X1, X2, 3, and 4, the most that X3 can be, and because it's free, you can assign it any value, there's going to be a restriction right here in X1. X1 has a subtraction. 50 minus what equals 0. Recall from the description of the problem, we have to assume there are no negative values. It said all values are non-negative. So to keep this from being negative, X3 has a cap at 50. And so that's the answer to that problem. The maximum value of X3 is 50, because if you go any higher, then you get a negative value. Please email me with questions or concerns. I'm here to help.